Welcome everyone to the Colloquium. Today we're happy to have Professor Seung Lee from Seoul National University who will talk about algebraic combinatorics. Let's welcome Professor Lee.
So my talk is twofold. For the first half, I'm going to talking about what algebraic combinatorics means to me from my point of view, and for the second half, I'm going to talking about Lustig theorem multiplicity. This is from representation theory, and I think this is probably why the Valentine invite me here. But I want to be more elementary, so in this for the colloquium purpose. So I wanted to start from the first topic, which is about algebraic. Okay, so I'm gonna start with the what is combinatorics. I'm not saying that I have a concrete definition of what this means, but when somebody asks me what I do for a living, then I say maybe I'm a professor or mathematician. But if you are already a mathematician, you might ask what more about what kind of subject in mathematics I want to study, and I do say combinatorics. And it is when there are many different ways of describe combinatorics, but the most important thing is obviously about content. For example, when you're if you're like 10 years old and you want if I want to explain to a kid, and that's the only probably the first word that I should say. But the problem is that defining what counting means is actually already ambiguous. So let me describe two examples. So the one which is easy, one which is hard. So let's say you want to count the number of vertices of n-dimensional cube. Cube means like this. So it's a three-dimensional cube. So vertex means this thing. So it's clearly, I hope everyone knows, this is the answer. This is 2D. So it can be the counting of the left-hand side. But sometimes you have some finite set which is not easy to compute. For example, let's say number of prime numbers less than equal to 10. So it's a hard problem because it's not, unless you specify n, it's not going to be, it's clearly it's finite set, but you don't know how to count for any. But I mean, exactly at least I don't know to precisely describe this combinatorially, but no materials know that this roughly grows as this function. So I'm not sure this should be considered counting or not, but because it's not exactly the same, but it tells already enough about these features of the primes. But so that's the two extreme examples that I have in mind. But my point is that it's not clear what the counting. So let's say you have some function, but for any natural number, let's say x is that thing, then there is this. I'm not sure. Maybe some people consider this, or some people does not consider this a constant. But I don't know. I don't have a strong opinions. But even when you have equality, strict equality, this is not 2 together is not a polynomial in n. So if let's say you somehow know, let's say you claim that you know how to combinatorially describe this. That means that probably means that it's some combination of let's say rational functions or polynomials on n. Maybe you want exponential function. Sometimes you want factorial. Sometimes you want like I don't know. There are many. But the point is that since if you want to claim that this does count something, it has to be negative, which should be clear from the right hand side. So there are many kinds of counting problems, but the reason why I brought this example is to distinguish between equality or asymptotics, or maybe both. Let's say you have same on like the first question. I mean, I can make the problem harder by replacing n dimensional cube by some other polytope, but my point is that when you have some conjecture about A equal B, you probably need algebraic techniques. As opposed to the case when you have this or this, then you probably want some more elementary, more analytic techniques. So that's what I want to point out. So what I mean by algebraic combinatorics is the best case when you have equality. The scenario is when, let's say I have some finite set I want to compute, which is usually hard. Or so let's say that's something you want to count. If I want to understand this from algebraic combinatorial point of view, that means I probably have some bijection, or let's say if the A is a set, then I mean the bijection between A and B, where B is something you already know. Or and to a clear positive. I think that's the best scenario. So let's say you are facing some accounting problem in your area, and you actually want to describe something, and one of the best cases is to find the right set, which potentially have many algebraic structure that tells you of more than just the counting, more than just the parameters. So I consider this as a problem of algebraic combinatorics. Algebraic. Yeah. I'm not saying this is all of them, but I think this is the easiest case of algebraic combinatorics.
Can I have a question?
Yeah, sure.
Is there any subject which is called analytic combinatorics?
That's actually a good question. So actually, the term algebraic combinatorics didn't exist before 1970s. Okay. To answer your question, so there are some it's called the additive combinatorics, which possess some analytic point of view, but I don't think people use analytic combinatorics because it's not that easy to define what they are. But the reason why people start using algebraic combinatorics term is due to Richard Stanley, which he gathered the many combinatorics from different area and combined so that he worked purely on combinatorics and gather the structures, study combinatorics, and get some systematic understanding of each combinatorial structure and apply it back to the area. So I think before him, the term algebraic combinatorics didn't exist, but since the Richard Stanley and many people got interested in combinatorics even without knowing the other area in mathematics. But I often do interest in the combinatorics because it's other area. So that's okay, I hope this answered the question. And But I said, okay. So going back to here, so I'll say that's the easiest case. So that's the thing there's a reason why I like algebraic because let's say we have something hard. Sometimes you are working on something called A, and let's say you have some other mathematical object, which is also hard. And there is equality between these two. Let's say, first of all, it's not possible to connect A and B before knowing both A and B, right? So let's say you have a studied geometry. Let's say you have this is some dimension of some finite vector space, and let's say, the first thing you do is usually calculate this dimension or this number combinatorially. That's what usually happens when you start with some A, connect this thing with something easy, something you already know. Then sometimes if you're lucky or if you're good enough, then sometimes you suspect that this number actually appears some different area. And if all things are working nicely, then you may find the relation between A and B without relying on combinatorics. So that's what. So for the first part of my talk, I have two keywords. The first one is about equality. So algebraic combinatorics is all about equality. And the way to use algebraic combinatorics in mathematics is usually often by finding a nice connection between two different areas or two different objects by studying underlying combinatorics. So I will call this connection.
I have a question.
Yeah.
So this equality means one-to-one.
Yes.
So my question is, if A and B may have like a algebraic structure, like a ring or group, vector space, does it may help? Did it help?
It does have a lot if your C is nice enough. For example, I mainly use the term counting, but what I actually do, C's usually it's just more than finite set. It has some action. It has some. I will bring one example, but Usually C has a nice algebraic structure. So let me put this, and that helps both concepts. So I think that's these two keywords the thing I want to describe is that this understanding this easy stuff helps you to understand both ends. Let me just put it this way and move on to my second part.
Maybe you can use the middle board.
Oh,
Because
I didn't know there was a middle. Thank you.
they're up and down. But the bottom board you cannot.
Oh, okay. Oh, I see. Thank you. I didn't know that. Okay, so I'm going to move to my second part. So I need to before I define, I need to. So I don't assume many mathematics while I try to define it. So let me just say that this is a Q analog of wave multiplicity, which I will describe soon. Which means that when I will have some polynomial in Q, non-negative polynomial in Q, and when you set Q equals to 1, it sends to this wave multiplicity, which I will define. So I need to start from representation here, I guess. So I'm going to assume that my vector space is finite dimensional. And usually when you talk about representation, it could be finite group or B group or the algebra. But in my talk, it will be either G9. Now we start with the GLM. Okay. So definition is groupomorphisms from G to GL3, where this is called this is finite dimensional vector space. So this is this is mapped from V to V automorphism. So it's a group, and left-hand side is the group, and this if this is the groupomorphism, that is called the finite dimensional representation of G. And when G is GLM, sometimes I need usually I need some subset representation, which is called the polynomial representation. But I'm not going to use this word again. So what I really mean in this talk is a polynomial representation, but I want to skip this word. Let me start with the well-known fact is that in our case, V can be written as a fraction of something called here this representation. So irreducible means that you cannot decompose photos. So we in this game, what I mean is that it's either GLN or C or S continuous. And in that case, it is enough to understand the irreducible representation, classify all the irreducible representation. Then all other finite dimensional representation will be interaction of these things. So by this fact, it is important to understand what the irreducible representations are. And for the case of GLM, irreducible representations are indexed by lambda, where the lambda is called a partition. Let me example. Let's say let me give one example. So this is partition is a weekly decreasing sequence of positive integers, and I usually write this diagram so that each cell, the first row, the number of cells in the first row is the lambda 1. This is lambda 1, 2.
You're missing one cell.
Oh, thank you. And here the lambda, where the m comes from is the bound of height. This height is in this case 3, and I want the height to be less than equal to m. And I'm gonna call this representation by V lambda. Which will be my main object. Instead of describing all these irreducible representation, I will just give one example. Those as a vector space. So M is 3. Let's say I want to this is C vector space, but I'm just going to write it there. So particularly just well-behaving nut basis, which is something like this. So as a vector space, this is 8-dimensional, and then these are the 8 vectors indexed by a certain filling on this shape, the Ferri shape of 2,1. With the numbers are there are three conditions. So all numbers in this thing is in between 1 and 3 in this M. And for our part, when you fill the positive integer, when you read rows is weekly increasing. When you read columns, it's increasing. These are the condition for this integers, positive integer in this. And I want to count more than just the dimension. So for each this base element, I'm gonna impose some monomials. So what I do is that the exponent of x1 is the number 1 used in this set. This top, I call this top. So this is these are the 8 monomials, and the claim is that there is something called the character of representation, so that when you compute, this is sum of 8 monomials in this picture, and this is also called the Schur function. So I gave an example for this thing, but a definition of Schur function is indexed by partition is a set of, by definition, set of for this kind of object, which is called the semi-standard Young tableau shaped lambda. Then I count some weight.
This is the last one, the 233. The
Did I make a mistake? Oh, sorry, this. So this is called Schur function, which appear in many places. Since there are finite in many number of vertices, the number of variables, this is also called polynomial. Sometimes you allow infinite many variables, and it's gonna be called Schur functions. So or let me add one thing. So now I can define way more goes to this. Oh, let me just write this notation. By definition, the coefficient of x means or Schur function. confusion. So you just very multiple is just count from combinatorial, you just count certain for example, this corresponds to the Schur function s 2,1, and there are two x1, x2, x3. So weight multiplicity for v 2,1 at the weight 1,1,1 is just number just 2. That's the combinatorial definition, which means that it's clearly positive. Let me tell you another formula. And I'm going to write this in the more general setting. Although my group or algebra is always either GLN or SP2. So I need to explain quite a few details since I wrote this in more general form. So the double is a Phi group, but in our case, it's a symmetric group, not in the SF essentially. Or it's in more generality, this is it's called the right. I'm not going to define it, but for at least for GLM, this is very clear. And okay, this R prime is a set of possibilities. And there is something called rho. And this bracket notation means I take the coefficient of this thing in this huge. So I will relate this thing in my example. So example, this is n equals 3, G is G and 3. Then R plus is this. These are this within C3. This is the standard vectors in C3. Okay, so these are the R plus and the okay. Then now I want to relate this with my axis, x variable. Previous step, e to the this that is just a former e, former variable. I. For example, if you see it in this formula, if you see e to the e1 minus e2, and the right in this the xi language, it should be interpreted in terms of x1 divided. Did any catch up here? Up to here? I mean, this could be technical in full generality, but I do need to start from this definition.
Sorry.
Okay.
What does it mean by -1 powered by W?
Oh, okay. For symmetric group, this means length of W. So for permutation, there are even permutation, odd permutation. If it's even, it's one. If it is odd, it's two. And there is a sign for the general factor W. But for permutation, this is just a definition. Okay, so I gave two different ways of describing ring multiplicity for GLM. One is by just specifying what the bases are and what the weights are. Here is alternate sum of something. So the point is, one issue with this formula is that the nice thing about this formula is that I can generalize this to any other G, reductive with G, but the problem is that this has clear sign. So left-hand side is clearly positive, so right-hand side should be clearly positive, but so formula doesn't clearly tells me that it is positive. And this, some people they may not care this, but it will make an issue when I analyze. Now I can introduce.
So on the right, you just expand using geometric, like 1/1 - x is 1 + x squared, right? On the right of the formula.
I have to divide by something, but
No, sorry, I mean, on the right, you have a quotient. Like 1/1 -
oh yeah, that is just same as infinite sum of
Yeah, okay.
yeah. This by definition this is same as infinite sum of e to the some number times alpha. Thank you. Okay, so now let me define a loose Q multiplicity. When I use a Lie algebra notation, it should be either Lie algebra corresponding to GLM in this, but I'm gonna define it for general. So I'm going to write exactly the same definition, not definition, the right-hand side. Except that I add one new parameter, which I call Q. Yeah, that's the definition. And now I understand why I shouldn't use this bottom board. Yeah. Let me erase this part because I don't need this anymore. So it is a polynomial in Q. The coefficients are integers, and theorem is that coefficient are non-negative. But before I claim this theorem, let me do the example we did before. So this is when Q is equal to 1, this is 2, where I was counting the certain tabulo of the weight 1, 1, 1, which means that I use the number 1 through 3 exactly once in this shape. And if you compute this Q analog, you will get this thing where this corresponds to Q squared, this corresponds to Q. that's the example. That's the example. And the theorem is that this polynomial is non-negative. No, when I mean the when I say polynomial, it means that coefficients are unknown. And this proof uses affine consequence polynomials. So this is same as affine causalistic polynomial, and there's something called the intersection polynomial to show that this also actually counts some dimension of some finite dimension vector space. That's a theorem in general. But let's go back to the GLM case. So we have told this is Q is 1. We already know how to combinatorially count this thing. So to get the hope is that I hope to, for each combinatorial object, I want to assign some non-negative numbers so that charge of this, I call this charge, but some statistical charge, so that I just start with the same combinatoric set, and for each element, I input some non-negative integer, and I take a Q power of that number and take a sum to get this Q analog of this Q loosely Q multiplicity. What I describe is the theorem, which works for type A, which is done by many people.
Excuse me, could you explain one more time why this Q parents is equal Q plus Q scale?
Oh, so that's actually a theorem. So I need to describe the theorem. So that's not theorem. That's not theorem. I think many people contribute, but I don't know. This belongs to them. For GLM case, for each tableau, like I drew in the picture, there is some statistical charge. These are, in this case, non-negative integers. So that now right-hand side is clearly non-negative polynomial, right? So that's the theorem, and this discovery is statistic is classical symbol. So I'm gonna define charge when mu is 1, 1, 1, or in general 1 to the L. So let's say the key is 1, 3. Let me. I think I need a board for example. Three. So there are many equivalent definitions, but I want to write this in terms of sequence of word, so that, let me skip this. So I need to define some set called descent. I is in descent if and only if you see the place of I and I plus one, if I plus one is above I, then I is in descent. So descent of T is in this case, so what, so I plus one is right of I. So this is one is a descent. This is two is a descent. The charge of P is defined by so since there's one descent, one M is 3, so I charge is 2. This is charge 2. So that's all I have for type GLM case. So my main work is about Lustick multiplicity for SP2N. So that's what I want to understand. So now, let me just verify. I don't need this definition, but just for the completeness, I'm just writing. I'm not going to use this. G, oh G. So then I need to start from classifying Edith representations. Are indexed by the same. Same partition, same restriction. So I'm gonna call this below that one. I'm not going back to the private. I have about 50 minutes, so I guess let's forget about Q, and there are many candidates for the possible, the replacement for the Semester-Young tableau. I cannot name everything, but yes, I've mentioned Kashiwara Nakajima tableau, or maybe for type C, there's something called King tableau. And there are others. There are other many different models, but the model I'm gonna use is for something called semester oscillator. This is the combinatorics I want. So here, A, I mentioned this A, B, C. I don't think I have time to introduce B, but the A is a loose stream complexity. This is, I will call this SSOT. And this is my C. . So let's set Q equals to 1. So it's known that weight multiplicity can be computed in terms of king tableau, certain shape, certain weight. There is a nice bijection between this the king tableau and semi-sorted tableau, which is my theorem. Okay, so let me introduce what these SSTs are. So I'm gonna define it by comparing semi-state Young tableau and semi-state Olsen. Let's pick one of the semi-state Young tableau I described. I used 113. This can be considered as a sequence of horizontal strips. So I always start with the empty partition. Then I see the partition in sub partition of this partition where I only use ones. Now and then I only keep the shape. That's my first horizontal strip. I don't have any twos in here, so second one is doing nothing. And first one is the one box in the second row. So you can easily check that this corresponds to sequence of horizontal strip. Horizontal strip means that this subset, the cells where the eyes are in, form a horizontal strip, which means that there's no two boxes at the same color. That's the definition. So that means this shape is not allowed. It should be always like shape like this. Okay. So what is I'm going to define SSOT as a sequence of horizontal oscillating strips. So SSOT, sequence of oscillating. So let me describe. So let's say I have a given some partition. I first add some horizontal strip. So I add something. Let me do this. Okay. I add 4 boxes here. Then I delete another horizontal strip. So I delete some horizontal strip. So oscillating horizontal strip of size P is oscillating horizontal strip of size I is same as adding some horizontal strip of size P and delete horizontal strip size I minus P. And for example, my P will be 1. So I will either delete a box or add a box. I guess I only have time for the standard case. We need to do one example to help you understand. So I have to start with the empty set, empty empty partition. And since the shape is empty, I need to go back to empty. Shape is finite shape. So from here to here, at each step, I'm either allowed to add one box or delete a box. So there are true. And so these are the SSOTs, and this will be some subset of this will be the combinatorial object that will be here when B is type C in SP2N. For this example, let me just compute the charge. The new statistic also cover energy, which is the following. So since I'm either adding one box or deleting a box, I can write this sequence as a sequence of the number of the row index of this nth box. This is one. So I add one box to the first row. I delete a box at the first row. That I put negative one. Oh, sorry. I use the column index. And this one. So charge for type A, compute need to see where the distance are. The distance are the place where the numbers are strictly increasing. Although my notation uses this. And I'm gonna add one more quote for first. So these are where the distance are. So distance are 1, 2, and 3. And the charge is, so the formula was I was a descent m minus I for type A. It's the same here. So m is 4, which is the length. So 4 minus 1, 4 minus 2, 4 minus 3. Except when I see 1 tensor negative, this is counted twice. So in this case, descent set is 2, but so 4 minus 2 should be the usual charge. But since I see 1 tensor negative 1, I multiply it. And this is option. Let me write a full theorem, although I didn't identify all of them. This is conjecture by myself and proved with Dong-Young Kim and Chien-Jae. This I different. Now this is Semester Olsen tableau. I need to change lambda and mu a little bit. So if lambda is this thing, and G, and this thing is my. Okay. And then I do the charge. So this is here. So when Q is equal to 1, it is known that this calculate the shape lambda weight mu king tableau. And that's same as by my theorem, the same as the number of sinusoidal tableau of this shape and this weight. And then what I do on the right hand side is that I, for each commutator object T in here, I define certain non-negative integers so that Q to the power of this thing and take a sum is indeed a Q weight, least Q multiplicity for type C. So this, I call this accounting. So left hand side is non-negative by geometric, but to count, just to actually count what they are. So the best scenario is to generalize the known combinatorial model and define a nice well-behaving statistic so that Q to the power take a sum is the same thing. So this gives the combinatorial formula for loosely Q multiple type C. So defining this charge is actually quite hard. So loosely, let me KL, KL. This is SS of T. And I didn't write what T is. Let me just write, let's say a few words about this thing and the problem. So this is certain subset of certain affine crystal, affine. It concerns from certain finite dimensional module of the quantum affine algebra. It is known that when these lambda mu's are big enough, this subset of this is called the stable pair polynomials, and there was known bijection between this thing. And what I did is to find the proper subset on here, and this statistic comes from this work. There is a certain statistic called the energy function. And after I biject this with this thing, I simply took the energy function in this one. And that's actually the function. So it is bijection between this thing and something called stable KR. It's curve of this thing. And this is English. So okay. Yes, all right, let's start here.
Okay. Any questions or comments?
It is important that charge T, we know that charge T, a maximum value or minimum value or charge T.
When you fix this thing, yeah, it is input value, and that part is easy to compute. That's known. That was known. Yeah.
And this polynomial is symmetric. And
No, it's not symmetric.
thank you.
Yeah.
Any other questions or comments?
So can I interpret this as kind of deformation of classical, inequality?
What do you mean classical?
Is that when Q equal 1,
Okay.
the left-hand side has some
The
classical.
left hand side is just usual finite formula, and the right hand side is this when Q is equal to 1. This is the set I defined and studied, because this is the reason why I had to invent this is because this is natural compared with this thing.
But is there any kind of geometric interpretation of this?
Of actually, I don't know. You're asking basically whether energy function comes from geometry, but then I don't know.
Well, I mean, uh, yeah, something like that. But I mean, if it's so, you mean the right-hand side was not classically studied, so you invented this as
For type C, there was no such a thing as this statistic on neither on this or king table or KN table or any model that you already know. There was no such a statistic.
I see. But for GRN case, is
The
it?
GNK is already known for same table. Yeah, for GNK, yeah, already they are known for quite a while. Yeah, so that's when this Q, then this comes from whole little polynomial, which are well studied from representation theory, geometry, and so on. But I don't know this thing in terms of geometry.
So I mean, for then A type, is there any geometric?
Yes, for A type there is there it is, but I can discuss it later. But I mean this is going to be long. So it's related to the nilpotent cone.
I see. But then anyway, A type is it also can be understood kind of?
Yes, the A type is already known that for type A, it was already known that the energy function coming from this thing is same as charge defined by Laskin-Stubberger. That was proved for affine type A here. So, but I don't know from geometric point of view. I think energy function, the term energy function comes from physics, but I'm not expert on describing this what energy function is. But I don't think it's coming. I mean, as far as I know, I don't know any geometric.
Any other questions or comments? Yeah.
Is there a reason why it's called semi-simple, semi-standard? SS or T?
Oh, semi-standard just means that that's the question. So the notion of horizontal strip naturally appears when you multiply answer with the n of p, let's say p. And this is sum of here's sum of this mu, where the this minus this is horizontal horizontal strip of size p. For type C, there is a similar description. There is a natural way to interpret horizontal oscillating strip.
Is there a standard oscillating table? Why is it semi-standard?
Sorry, can you say again?
Why is it semi-standard?
That's because you, for example, let's do. So let's say you start from empty set for type A, then you do A, then B, then when you compute you start from empty set to this A, and then you tensor this, then you are forced to add the horizontal strip from here. When you write the numbers here, this is semi-standard. That's where the semi-standard condition comes from.
Oh, it's just
You just put a number for the which horizontal strip at which horizontal strip you have used, and you just put the numbers I, and you start from empty set. You keep adding and adding. Then this table I just made will be automatically semi-standard.
I'm not very familiar with the terminology, but so semi-standard is some terminology used in that field.
Oh, semi-standard. Young tableau is the standard terminology when you study representation of GLN or Schubert calculus for flat Grassmannian, but it is very standard terminology for type A. So since young tableau is very old thing, and so I mentioned I gave two definitions of shear function. One in terms of this tableau, weight based on tableau. One is just this thing. The shear defined shear polynomial by using my second definition. So the sure define this thing a little bit similar to the variable character formula, which doesn't possess the positivity naturally. But after him or other people describe each monomial combinatorially, and that's where the semi-standard Young tableau came from.
Is there a standard Young tableau?
Yes, standard means that numbers are used exactly once. So this is correspond to this tensor of this one, tensor of this.
Any other questions or comments? Okay, I have a few quick questions. When you say you relate to affine KR crystals, is it affine for GLN hat or SP hat?
That's a great question. So for GL, this is the same as GL. This is for type A, this type A, but this, let me call this type C. So this is type C. I have to use affine type B or D, they're the same. So actually, let's look at it. I'm using a different type.
Okay.
And that's, yeah.
So is B and D the same?
No, they're different. So but there are 4 types in this setting.
So can you not,
Oh,
I have a second question regarding that. But
oh, okay.
anyway, now it's okay.
So there are 4 types, like there are 4 different types in this thing,
Okay.
and somehow this type is different from the affine version of this type. I had to take a dual.
Like.
Yeah, down.
Okay. 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 And it's untwisted affine.
Yeah, on this. Yeah.
Okay. And the second question I had, this still, so like when you specialize in either situation, when you specialize Q equals 1, you still get the dimensions of these weight spaces for representations
Yes.
of SP.
Yes.
Okay. And you're saying these were known for Q equals 1 before, but the Q version is due to you and the other 2 people.
So when Q scope 1, you can replace this by some other object.
Okay.
I mean, so this in that sense is known for. I mean, for Q equal 1, it's known for every type.
Okay.
For like a Gaussian tablet for type ABCD.
Okay.
And so for Q equals 1, many people studied and well understood, but before me, no one made the right charge this statistic
Okay.
on any form of model.
Okay. And do you understand type B or D?
That's harder, and for D, I don't know. For type B, I do know for spin rate.
Okay.
So it gets complicated. So somehow type C is very nice because this inclusion is very nice.
Okay.
Usually this I actually don't know the right subset.
Okay.
I mean, once I find the correct subset, then Q comes from this word, which is automatically determined. So this, I don't know what this is. That's my issue.
Okay. Any other questions? No, let's thank the speaker again. I think we have some food in the room there.